We're in Physical Chemistry, Chapter 18, Section 2 now. Now we're going to talk about the photoelectric effect and photons. Now another red flag for classical physics was the photoelectric effect. Einstein actually got the Nobel Prize for this. So here's Leonard in 1900. So let's say we have potassium on a metal. And then here's H frequency. So this is light coming in. We have electromagnetic radiation coming in and knocking out electrons from their orbitals. So notice energy came in packages. The change in energy is going to be equal to the number of whatever, 0, 1, 2, 3, etc., times H times nu. Where nu, of course, is the frequency of the light coming off. And then H is 6.63 times 10 to the negative 34 joule seconds. So now let's talk about the kinetic energy of the ejected electrons. So Ke is kinetic energy, vertical axis here. And then the horizontal axis is the frequency of the incoming light. So if you had low frequency light, no electrons came off. Then when you had higher frequency light coming in, you would get more energy of each electron coming off. So there was some sort of threshold frequency, like a minimum frequency, to knock an electron orbit, knock an electron off the potassium. So we call this nu naught the threshold frequency. Now, classical physics says that electrons, they would eject into any light. Let's say here's the number of electrons, here's light intensity, and you just get a straight line. More brighter light means more electrons. And then the kinetic energy of the electrons, no matter what, how bright the light is, you would expect, by classical physics, that all the electrons to have about the same kinetic energy. So what happened violates classical physics. In classical physics, the energy of each wave is just going to be proportional to the intensity. So I is intensity, and then this E type symbol, I think it's epsilon, I'm not sure, it's amplitude. So the intensity of the wave is proportional to the amplitude squared. Now in the year 1905, I know normal people pronounce it 1905, but anyway, Einstein said electromagnetic radiation, or light, comes in elementary units called quanta. And it is the energy of the elementary unit, not the total energy, that determines whether an electron is liberated or not. So G.N. Lewis called these quanta photons. An analogy, let's say that we have 2,000 machine gun bullets, but they'll cause no damage to a target wall. But if you have just one big 15-inch shell, that'll destroy the wall. Same sort of thing. So here's voltage versus frequency. So again, low frequency, nothing will happen. But past the threshold frequency, then you're going to get voltage off. So H nu is going to be H nu naught plus Ke, where Ke is kinetic energy. We're going to H nu is equal to H nu naught plus 1/2 mv squared. And of course, in this case, lowercase v is the velocity of the electron, because this was the kinetic energy of each electron coming off. So Ke is going to be 1/2 mv squared, and that's going to be equal to E times voltage. So we have two different v's here, velocity or speed, and then voltage. So, and then E is just the charge of the electron. So charge times voltage is equal to energy. So we get H nu is equal to H nu naught plus the charge times the voltage. So we get H nu minus H nu naught is equal to E times the voltage. So to solve for voltage, we get H over E times nu minus nu naught is equal to voltage. So the slope of that graph is equal to H over E. Now we know E, so we can find out H. Now remember, in case I didn't mention, H is Planck's constant. So we get Planck's constant times the frequency of the photon is going to be equal to phi plus 1/2 mv squared. So phi is called the work function. and it's equal to h nu naught. So phi is the minimum energy it takes to eject the electron from the substance. So 1, if h nu photon is less than phi, then there is no photoelectric effect. The light just gets scattered. 2, if nu naught is equal to constant for a given metal, then you get phi is equal to h nu naught. Phi is constant. If h nu photon is greater than phi, then as the frequency increases, so does the kinetic energy of that one ejected electron. Now let's talk about red flags of classical physics. 1 was heat capacity. 2 was blackbody radiation. And 3 was the photoelectric effect. So the photoelectric effect, it proves that light is a particle. Now light is actually very complex. For one thing, light has wave properties. For example, diffraction, which means when you scatter it using multiple centers, kind of like neutron diffraction. Electrons can also undergo diffraction. So that means electrons can also behave like waves. For example, here's two walls. Here's a wall with a hole in it, and here's a screen. Light comes through this one hole, then it radiates outward from that hole, and then what you see on the screen is a bunch of concentric circles. 2 is interference, which means scattering by a few centers. And the particle property of light, though, 1 is the photoelectric effect. Energy is equal to h nu. Remember, nu is frequency. E is the particle concept, but nu is a wave property. And frequency is a wave concept. So what this is equating, a particle property with a wave particle property. And then there was the Solvay conference at 1927.